Have you ever, pictured a future where tech just kind of knows what you need, handles things without you even asking? Or maybe when you're using your smart speaker or phone, you stop and think, hang on, what's actually happening inside this thing when it seems to? Well, think.
Hmm.
Welcome to the deep dive. Today we're going to try and cut through some of the hype, the buzzwords flying around. We want to unpack the real difference between standard automation and advanced artificial intelligence. We'll dig into what they are, how they really work under the hood, and maybe most importantly, what it all means for jobs, for our lives, really. So, our mission today is to get really clear on this line between, let's call it dumb automation, the systems just following orders, basically, and the smart systems, the ones that can actually learn and adapt. It matters a lot for understanding how tech is, well, changing everything. And we've got some fascinating research to help us figure it out.
That's right. It's about looking past just what these systems do and getting into how they operate fundamentally. And maybe just as crucial, what they can't do yet, their limits.
Okay, so let's set the scene first. When we talk about traditional automation, that's these dumb systems, right?
Hmm.
Machines doing exactly what they're told, following very explicit, pre-programmed rules, super precise, but no real brains behind it.
Exactly. Think about a classic computer science puzzle, the missionaries and cannibals problem. You got to get everyone across the river, but the cannibals can't ever outnumber the missionaries on either side.
Yeah.
Now, a computer program solving this just follows strict rules we give it, like max 2 people in the boat, keep the missionary count higher or equal, that kind of thing.
Yeah.
It's just moving symbols around based on logic. It has zero idea what a missionary or a cannibal actually is, or even a boat, for that matter.
So it's like this incredibly efficient rule follower, executes perfectly but doesn't get the why at all, brilliant at its specific task, but breaks if anything unexpected happens.
Totally brittle, yeah. You can keep adding more rules, trying to cover every possibility, but you're always just patching it up.
You're not fundamentally changing its nature.
Exactly. It's still just following instructions. And that's where artificial intelligence comes in as a different beast entirely. These are the smart systems.
Hmm.
AI is really about creating algorithms that can learn from data. They kind of program themselves in a way.
Right, and that's the game changer. That's the key difference, isn't it? The machine isn't just stepping through a list we wrote. It's looking at data, finding patterns, making decisions, learning from experience, almost like we do. And all the really dramatic stuff we've seen lately, image recognition, understanding language, AlphaGo beating the world champion, that's all this AI, specifically deep learning, right?
That shift from hard-coded rules to learning from data, that's absolutely the core idea. And machine learning, or ML, is the engine driving it. It's the part of AI where the algorithms actually do the learning based on the data they see.
Okay, so how do they learn? Is it like teaching a kid or is it more complicated math?
Well, there are a few flavors, but the most common one is called supervised learning. And yeah, thinking of it like teaching a kid by example isn't a bad analogy. You show the machine, say, a picture of a cat, and you tell it, that's a cat. You give tons of these labeled examples. Input X goes with output Y. The machine's job is to figure out the connection.
Ah, like the spam filter in our email. I saw in our sources something about an SVM model doing that. Can you give us the quick gist of how that works without getting too technical?
Sure. Think of an SVM that's a support vector machine, like it's drawing a line or a boundary in the data. It learns which words or features are important, assigns them weights, and uses a bias to help it decide, okay, stuff on this side of the line is spam, stuff on the other side isn't. It's basically a smart categorizer learning from all the examples you fed it.
Hmm.
Same idea for recognizing, say, a specific dog breed in a photo.
And I bet you need a lot of examples for that to work well. You mentioned ImageNet earlier. Wasn't that about training on millions of pictures?
Millions, yeah. That's the thing. Supervised learning needs massive amounts of human-labeled data. That's a huge bottleneck. Experts like Andrew Ng, Yoshua Bengio, they've both pointed this out. Getting all that labeled data is a major, major challenge if you want AI that can learn about anything and everything.
Yeah, I can imagine. Labeling millions of photos sounds tedious, to say the least. Okay, so that's supervised learning. Needs lots of labels. But the real buzz is around deep learning. What's the deal with that? Why is it the hot thing?
So deep learning is actually a type of machine learning. It uses something called deep neural networks.
Hmm.
Think of layers upon layers of interconnected nodes, kind of like simulated neurons. They're inspired by how we think brains are structured, inputs, processing outputs, connections with different strengths or weights. But it's important to stress it's an inspiration, not a copy. They don't work exactly like our brains.
Okay, inspired by the brain. And what makes them deep and so powerful?
The deep part refers to having many layers. This depth allows them to learn really complex, intricate patterns in data things that aren't just simple linear relationships. Now, neural networks aren't new, they've been around since the 50s, but they kind of fell out of fashion. What changed, really around 2012, was suddenly having access to huge data sets like ImageNet and the computing power, especially from GPUs, graphics cards, to actually train these deep networks efficiently. People like Hinton, LeCun, Bengio. They were key in bringing them back and refining the methods, especially something called backpropagation, which is how the network learns from its mistakes across all those layers.
Fascinating history there. It wasn't just one breakthrough then. And I read something really surprising that tuning these deep networks, adjusting the settings, it's described as alchemy, an art form.
Yeah, it's kind of funny, isn't it? But it points to something real. Setting those hyperparameters, the dials that control the learning process itself, isn't always straightforward. It often involves intuition, experimentation. It's not always clear why certain settings work best. Folks like Demis Hassabis or Eric Horvitz, who are right at the forefront, talk about this. It suggests that even with these super smart machines, there's still this element of human craft and experience needed. Maybe only a few hundred people worldwide really have that deep intuitive grasp right now.
Wow. So human intuition is still key. Okay, so supervised learning needs labels. Deep learning finds complex patterns. What else is there? You mentioned another way machines learn.
Right, there's also reinforcement learning. This one's quite different. Instead of labeled data, you have an agent, like a robot or a program operating in an environment, often a simulation. It tries different actions and occasionally gets a reward or maybe a penalty. It learns over time what actions lead to the best rewards. Think trial and error, like training an animal with treats.
Okay, so like the example of Rosie the robot learning to kick a soccer ball, it tries, maybe falls over, tries again, gets a tiny reward if it nudges the ball, and it keeps track in a Q table. What's that?
A Q table is basically its memory of what worked where. It's a big table mapping situations like where's the ball, where are my legs, and actions, kick left, swing right, to an expected future reward, the Q value. It learns by updating this table based on the rewards it actually gets. And the most famous example of reinforcement learning is definitely AlphaGo, DeepMind's program. It learned to play Go at a superhuman level, mostly by playing millions and millions of games against itself, refining its strategy based on winning or losing. And what's even more amazing is the successor, AlphaZero, learned chess and shogi the same way, just given the rules and playing itself. No human game data needed.
That is just mind-blowing, but those Q tables sound like they could get ridiculously big for real-world stuff, right? Like driving a car. There are infinite possibilities.
Exactly, that's the catch. Simple Q tables don't scale to complex, messy reality. So in practice, deep neural networks are often used within reinforcement learning to approximate that Q-value function, to estimate the reward without needing a giant table. But even then, reinforcement learning has had its biggest wins in controlled environments, like games. And sometimes the solutions it finds are weirdly specific, kind of brittle. Like there was that AI trained to play the game Breakout, got superhuman scores. But if you shifted the paddle just slightly, its performance crashed. It hadn't really learned the concept of hitting the ball with the paddle. It had just found a very specific, optimized sequence of actions for that exact setup. It lacked generalization.
That really shows the limits, doesn't it? It's not true understanding. Okay, so what about the last type, unsupervised learning? Is that the key to getting past these limitations? The holy grail?
A lot of researchers think it might be. Unsupervised learning is about learning from data that hasn't been labeled. The system has to find structure and patterns on its own.
Ah, I see the appeal. Because that's more like how we learn, isn't it? Especially as babies, we just watch and listen and interact and figure things out without someone labeling every single object and action.
Exactly. That's why it's seen as crucial for developing real common sense in AI, learning the underlying structure of the world from raw observation.
But it sounds hard.
Oh, it is. It's one of the biggest open challenges in AI right now.
Hmm.
We're still quite far from machines that can learn about the world in that rich, unsupervised way that humans do so effortlessly.
Okay, so even with all this progress, image recognition, games, translation, these smart AIs, they still have weaknesses. Big ones, maybe. Where are they still, well, kind of dumb?
Well, the biggest conceptual limit is this idea of narrow AI versus artificial general intelligence, or AGI.
Mhm.
All the AI we have today is narrow AI. It's task-specific. Fei-Fei Li makes this point very clearly. Current AI is fantastic at pattern recognition within a defined domain. It can spot the Dalmatian or win at Go, but that skill doesn't transfer. The Go-playing AI can't suddenly decide to, I don't know, write a symphony or offer relationship advice.
Right, it's specialized. AGI is the sci-fi dream, isn't it? A machine that can think and learn and reason like a human across many different areas, like C-3PO or data from Star Trek.
Pretty much. And when you ask experts when we might get AGI, well, the answers are all over the place. The general consensus is it's a long way off. You hear estimates like decades, maybe even a century.
Mm-hmm.
You have optimists like Ray Kurzweil, who thinks maybe 2029 isn't impossible. Then you have people like Rodney Brooks, who are way more skeptical, suggesting 2200 perhaps. Yoshua Bengio talks about it not being one single hurdle, but a series of other hills to climb. Ornetzioni agrees there are many, many unsolved fundamental problems. The takeaway is we're not just talking about needing faster computers, we're missing key scientific insights.
So it's not just around the corner. And besides being narrow, what else are they missing? You mentioned common sense earlier.
Yeah, that's a huge one. Current systems, especially deep learning ones, are surprisingly bad at common sense reasoning. Abstraction, using analogies, thinking about what-if scenarios, counterfactuals, or really understanding cause and effect, they just don't get the world the way we do.
Can you give an example of that? I think Barbara Gross had a good one.
She did. She said, if a machine really understood the sentence, "the printer is broken," its response shouldn't just be to record that fact, it should be to initiate actions to get it fixed, understand the implications. Or think about those visual puzzles called Bongard problems. They show two sets of simple diagrams, and you have to spot the abstract rule differentiating them. Humans are usually pretty good at this, even with few examples, because we can abstract and see analogies. But AI, even powerful visual systems like ConvNets, struggle massively. They might need thousands of examples just to learn a simple concept like same versus different that a child grasps quickly.
And Ornetzioni's plant example too, right? An AI wouldn't inherently know moving a plant near a window might make it grow faster because it lacks that basic world knowledge about sunlight for plants.
Precisely. It doesn't have that built-in intuitive physics or biology. And this ties into the black box issue Judea Pearl talks about. Because deep learning models learn statistical correlations, not causal relationships, their reasoning is often opaque. It's like complex curve fitting, he says. We see the output, but we don't truly understand the why behind it in a way that makes sense to us.
And if we don't understand the why, can we really trust them? Especially for important decisions, which kind of leads to another problem. How vulnerable are these systems?
Very, in some surprising ways. They're susceptible to adversarial examples. These are tiny changes made to the input, often totally invisible to humans, that can cause the AI to make a huge mistake. Think specially designed glasses, making someone invisible to facial recognition, or small stickers on a stop sign, tricking a self-driving car into seeing a speed limit sign. There was even research showing subtle noise added to medical images, like X-rays, could fool an AI into wrongly diagnosing cancer with high confidence. It shows their perception is fundamentally alien to ours and brittle.
Wow, that's unsettling. It's not just about being fooled maliciously either, is it? What about bias?
That's a massive concern. Fei-Fei Li and others have stressed this. AI learns from data. If that data reflects existing societal biases, racial, gender, whatever, the AI will learn and potentially amplify those biases. If your training data for hiring algorithms mostly shows men in executive roles, the AI might learn to discriminate against women, even if that wasn't the intention. The consequences can be serious.
So, these ethical issues, trustworthiness, bias, vulnerability, explainability, they're not just future problems, they're now problems.
Absolutely. Barbara Gross and Josh Tenenbaum make that point strongly. We need to focus on building reliable, fair, understandable AI now, not just worry about hypothetical superintelligence decades away. It really forces us to ask, what kind of AI should we be building? How do we ensure it benefits everyone?
Okay, let's bring this down to earth then. Thinking about that automation versus AI distinction, how is this actually playing out in the real world? What's the impact on jobs, on society?
Well, Stuart Russell talks about the humans as robots problem. Basically, any job that's highly repetitive and predictable, where a person is just following a strict process that's ripe for automation, whether it's by a physical robot or just software, that's the dumb automation replacing routine tasks.
But AI changes things, right? Martin Ford says we're at an inflection point because AI isn't just automating manual labor, but cognitive tasks too.
It's exactly. It's moving into areas that require pattern recognition, data analysis, even some forms of decision-making that we used to think were purely human territory. Now, the impact on jobs is complicated. James Manika's work at McKinsey suggests it's not just jobs lost. There will likely be more jobs gained overall, but also huge shifts, Lots of people will need to transition. The key thing they found is that vulnerability isn't just about low-skill jobs anymore. Tasks involving data collection, processing data, and predictable physical work are most at risk, regardless of the wage or skill level usually associated with them.
Okay, so what kinds of skills or tasks are safer then?
Things that require complex judgment, creativity, managing and developing people, interacting with others empathetically, and dealing with unpredictable physical environments. These are harder to automate, at least with current AI. And the solution everyone points to is continuous learning. Daniela Rus, Jan LeCun, Ray Kurzweil, they all emphasize education and retraining. We'll all need to be lifelong learners to adapt.
Lifelong learning becomes the norm. And what about society as a whole, beyond jobs?
There are big questions. Andrew Ng raises concerns about AI concentrating power in the hands of a few large companies or governments that control the data and the technology.
Makes sense. What about regulating AI? Is that feasible?
The consensus among many experts, like Jan LeCun, seems to be, yes, regulation is needed, but it should focus on the applications of AI, like how it's used in self-driving cars, or medical diagnosis, or finance. We already regulate those areas. The ideal is to adapt existing frameworks rather than trying to regulate the fundamental research itself, which is much harder. And crucially, it needs input from everyone, not just the tech folks. And this feeds into the broader optimism versus pessimism debate. You have someone like Ray Kurzweil, who sees technology, including AI, driving progress, peace, maybe even abundance, pointing to how past industrial revolutions ultimately increased overall prosperity and employment.
But then you also have thinkers like Nick Bostrom raising flags about the long-term risks, the control problem. What happens if we do create superintelligence and its goals don't align with ours? That's a whole other deep dive, maybe.
It really is. These are huge, ongoing discussions with very smart people on all sides.
Okay, so we've really tried to unpack this today. The crucial split between automation just following rules, the dumb stuff, and AI that actually learns, the smart stuff. We've seen how powerful that learning can be, recognizing faces, mastering games. But we've also hit on its very real limits right now. The need for tons of data, the lack of real common sense, the brittleness, the biases. Smart AI is still narrow, still quite different from us. So here's a thought to leave you with. As this line keeps blurring, as machines get better at executing and learning, what does that mean for us, for our unique human skills? If machines can learn and adapt, maybe our value isn't just in what we do, but in how we choose to work with them. And in a world where AI can learn from endless data, what happens when we humans fully embrace lifelong learning alongside these machines? What new kinds of intelligence might emerge from that partnership? Maybe the real deep dive we need is into ourselves and how we adapt.